final major topic we want to discuss here is the difference of two proportions. This is very similar to the difference of two means, but with a slightly different formula for calculating the standard error. But conceptually, it's very similar. Here's our formula. Notice that, in general, we're calculating the difference of two proportions in the numerator, and we're dividing by a standard error. This is very similar to the difference of two means. Let's look for a moment at the calculation of the standard error. This is different than the difference of two means problems we did before. We have sigma hat, so we know that this is an estimate of some kind of standard deviation, sub p sub 1 minus p sub 2. This tells us that it's an estimate of the standard error of the sampling distribution of two proportions. The formula itself is pretty simple. It's p asterisk times 1 minus p asterisk times n sub 1 plus n sub 2 divided by n sub 1 times n sub 2, and then we take the square root of that whole product. The problem here is to calculate p asterisk. We have to do that before we can do anything else. P asterisk is simply the weighted average of the proportion of ones. Let's look at a concrete example and show you how to calculate the difference of two proportions. That should make this clearer. In the General Social Survey, we have two variables that we're interested in. The first one is, do you favor or oppose the death penalty for persons convicted of murder? People can either favor or oppose the death penalty. We also have a variable that measures party ID. People are asked whether they think of themselves as Republicans, Democrats, Independents, or something else. I've changed this and recoded it, and I've extracted only the people who identify as being a strong Democrat or a strong Republican. In 2010, there were 174 strong Republicans, and 86% of them believed in the death penalty. In 2010, there were 301 strong Democrats, and approximately 49% of them believed in the death penalty. The research question we're trying to answer here is the 37% difference between Republicans and Democrats who favor the death penalty statistically significant. Let's put this into our hypothesis testing template and format. Number one, we have to assume the null hypothesis of no difference. Here my null hypothesis is that mu sub d minus mu sub r is equal to 0. That is, there is no difference in the proportion of Democrats and Republicans who favor the death penalty. My alternative hypothesis is mu sub d minus mu sub r is not equal to 0. This indicates that I'm using a two-tailed test. I'm not interested in which party is more favorable of the death penalty, but simply that they are different from each other. Step number 2. What's our sampling distribution or picture of chance? The good news is, like a difference of means test, when we do a difference of proportions, we can use the t-distribution. So anytime we're confronted with a problem where our dependent variable is a proportion and our independent variable is a dichotomous variable, we use the t-distribution as our picture of chance. Step number 3. How much evidence do I need to reject the null hypothesis? How big a difference is required to conclude that Democrats and Republicans hold different opinions about the death penalty? I'm going to use an alpha of 0.001, which pushes us way out into the tails of the distribution. The implication of this is that it's going to take a bigger difference to reject the null than if I'd used an alpha like 0.05 or 0.01. I go to my t-table in the back of the book. I have 473 degrees of freedom. That is, the number of Republicans plus the number of Democrats minus 2. And I look up the column where alpha is 0.001 two-tailed. I find out that my t-statistic is approximately 3.291. Again, this is a number you should have been able to come up with on your own, knowing that we typically use, for large samples, 1.96, 2.58, and rounded 3.3. Step number 4. We've got to go to the real world, collect our data, and calculate some statistic. We're going to show that on the next slide. We're using the General Social Survey data, and I'll provide all the summary information and calculations on the next page. Our last step in hypothesis testing is to take the t-critical we calculate in step 4 and compare it to the t-critical we found in the table in step 3. That is, we're going to calculate t-calculated, and we're going to compare that to approximately 3.3. Here's the information we know so far. Approximately 86% of the 174 Republicans favor the death penalty. Approximately 49% of the Democrats, of the 301 Democrats, favor the death penalty. Our T-critical is 3.3. Let's first calculate the standard error. Remember, to calculate the standard error, the first thing you need to do is calculate P asterisk, which is the weighted average, in this case of 86.21 and 48.48. Plugging it into the formula, my P asterisk is 0.623. Obviously, I can calculate 1 minus 0.623 and start plugging these numbers into my T formula. The numerator is simply the difference of the proportion of Republicans and Democrats who favor capital punishment, and then all the other numbers are taken right out of the table above. And I get a T statistic of 8.17. My T critical was 3.3. 8.17 exceeds that value, and so I'm going to reject the null hypothesis and conclude that when it comes to capital punishment, there's an ideological gap between people who are identified as strong Republicans compared to strong Democrats. Let's look at another problem. This one has a little bit smaller sample, and it's not taken from the General Social Survey. A researcher went out and asked men and women if they had received a $100 bill in their mail, but it was addressed to their neighbor, would they return it to their neighbor? We calculated the percentage who would return the money to their neighbor. For example, of the 69 men who were surveyed, 52 of them, or approximately 75%, said they would return the money to their neighbor. Of the 131 women who were surveyed, 120 of them said that they would return the money to their neighbor. That's about 92%. So for this problem, we're going to compare or test for a statistically significant difference between approximately 75% for the men and 92% for the women. I'm not going to put this into the hypothesis testing format. I'm going to leave that up to you, but I'm going to show you all the calculations again. As a reminder, here's our formula for the standard error. By itself, not too difficult, but remember the first step is to calculate P asterisk, which again is simply the weighted average of the proportion of people who would return the money. On the left bottom of the screen, you can see I've gone ahead and done that. I find that the average proportion of people who would return the $100 is 0.86 or 86%. 1 minus that is 0.14. That is, approximately 14% of the people on average would not return the $100 bill. Those are weighted averages and they ignore gender. I'm now going to take those numbers and plug them into my formula for my standard error and come up with a standard error of 0.0516. It's a little bit of a calculator issue. You have to make certain you understand orders of precedence and or use parentheses wisely. But in this case, the standard error is 0.056. It's pretty much downhill from here. We simply calculate the difference between men and women, that's our numerator, and divide by the standard error. And in this case, we get a T statistic of 3.15. Because I didn't put this problem into the hypothesis testing format, the 3.15 can be interpreted differently by different people. For example, if you selected 0.05 or 0.01 as your alpha value, you would reject the null hypothesis and conclude that men were less honest than women in this particular situation. On the other hand, if you picked 0.001 as your alpha value, you would fail to reject the null and conclude that men and women, by and large, based on our sample, show no statistically significant difference in their honesty with returning this $100 bill to their neighbors. It's not that one is right or wrong. Remember, the ability to set alpha lies with the researcher, and it's determined by their balancing of making a type 1 versus a type 2 error. Using a smaller alpha requires that you have a bigger difference and makes it harder to reject the null. And therefore, it decreases the probability of making a type 1 error. If making a type 1 error is costly, then you're probably going to want to select a smaller alpha value.